So we have our midterm exam this week. Log on to Dropbox anytime before Friday at midnight, Friday night, midnight. And you can just click that link and you'll have 75 minutes to take it. It's multiple choice and 20 questions. If you find anything strange, any typos or glitches in there, just send me an email and we'll get it fixed. Okay? Also, we have a quiz due at the end of this week, quiz 6 on control theory, assuming I finish the control theory lecture. If I don't, I'll just extend it a week. And then we have lab 3 is due on November 3rd, which is next Friday. How's lab 3 coming? Any questions or issues with lab 3? Okay.
It does not like connecting to the FPGA board. It doesn't like it.
Oh, we're still having JTAG issues?
It's not JTAG issues, it just can't find it.
You mean when you go to download the ELF?
Yeah.
Okay, I'll take a look at that after the lecture, if you've got a few minutes. Okay. Okay, so I think last time I started with this lecture, this is basically like a crash course on control theory. Control theory is the idea of having some kind of a controller, which in our case is going to be a microcontroller, exert control over something physical, something in the real world. So the thing you're controlling is called the plant, and the controller is the controller. And generally you have some set point, which is what you want. It's from the user perspective, what you want the plant to do. So if it's a robot, you may want to have it drive somewhere and stop or whatever. And then the plant is going to be subject to disturbances. So, for example, if you have a self-driving car, a disturbance could be, the road bends, or if you're controlling a drone, the disturbance might be a wind gust. And hopefully, your controller is able to still control the plant despite these disturbances. So we talked about the notion of open loop control, which is where your controller is connected to your plant, and it's an open loop. So this is how toasters work, which annoys the hell out of me, because you have a set point where you say, I want to have a certain color of your toast, and the controller is controlling the cook time and the temperature, and you calibrate the idea is that you calibrate the controller so the controller knows what to tell the plant to do based on the set point, but it doesn't always work, especially when you have disturbances, which in this case would be like different types of bread. Different types of bread toast at different rates, or brown at different rates, right? So another one that annoys me personally is the drying machine, which is where you have a set point. You say, I want you to dry my clothes. I want them to be completely dry, no dampness whatsoever. And the controller controls the dryer time and the dryer temperature. And you hope that the clothes are dry, but they usually aren't, at least in my case, right? Now you can fix both of these problems by using a closed loop controller, which is where you have some sort of sensor in the plant, or sensors, that feed back to the controller. And typically the way it's done, and it's not always connected in exactly this topology, but generally speaking, you'll have some kind of a sensor which will measure what's called a process variable or process variables, and you're comparing those to your set point. So your set point is generally going to be in the same units as your process variables, which in this case would be brownness of the toast. So I have a desired brownness, and I have an actual brownness, which is measured by an optical sensor inside the toaster. I mean, this should be possible, right? But apparently it's not. And so basically you're comparing them by taking the difference, and that difference is the error. It's basically how far off from the set point you are, and then it's the error term that's the input to the controller, not the set point as it is in an open loop system, but it's the error term that's the input to the controller, and then the controller has this cook time. So this way, with a closed loop, it's a more robust scheme, and it generally works better, and it's more resilient to disturbances, right? Okay, so As I mentioned, the process variables are the values that you're reading from the plant. The manipulated variable are things, the inputs to the plant. And then, of course, you've got your disturbances, and you've got the plant, which is what you're controlling, and the controller, which is the controller. So we see control systems everywhere. So the reason why I added this material to this course is because we have this sort of new generation of Internet of Things and cyber-physical systems, smart appliances, and everything is smart now. And in my assessment, when someone says that you have a smart whatever, fill in the blank, what they're really talking about is they just added a controller to the thing, right? So, and so for example, self-driving cars is a big deal. Of course, you've got things like, camera autofocus systems, which are always improving, smart thermostats and drones. These are all basically just, they seem like it's this new concept, but it's really just applying a closed loop controller to a system. So the problem is that this is a challenge, or can be a challenge to design a controller that works. This is why, for example, like SpaceX, they have the thing that impresses the hell out of me, which is that the rocket that actually lands, comes down from space and lands upright. And that's basically just a control system. But, there's been a high failure rate. Why? Well, it's because it's difficult to design a controller for that, obviously. If you can, if it was easy to do, then it wouldn't, you wouldn't have so many crashes of those rockets. And part of the reason for that is because you want to be able to, when you're designing a control system, you hope to be able to design it before you deploy it. But the problem is that in order to do that, you need to be able to model the plant. You need a model, you need a mathematical representation of what the plant is doing, and the disturbances, ideally. The problem is that plants, every physical thing in the world is non-linear. It's hard to model non-linear things. And so, at least in basic control theory, you usually start out by modeling plants as linear systems, as an approximation of the actual system. And then you hope that's good enough, a good enough approximation of the nonlinear system. So what I mean by that, when I say linear system, you might think of what I'm really talking about is a linear time invariant system, which is basically what that describes is an ordinary differential equation. You might say, wait a minute. That doesn't make any sense. A linear system is a straight line, right? But yet a differential equation is never a straight line. So how can that possibly be linear? That doesn't make any sense, right? Well, when you refer to linearity in terms of differential equations, what you're talking about is when you have a variable or a set of variables. These are time series variables. So like x of t. You could think of these as signals, like when you take electrical 222, these are referred to as signals. Some people refer to these as state variables, or others, but they're basically a variable with respect to time, right? It's a time series. And so you can take derivatives of that with respect to time, and you can take any derivative you want, first, second, third, fourth, or you could take an integral of that variable, right? And then you can also apply a constant multiplier, a coefficient to that, right? So you could say, for example, you could have the derivative of x with respect to t, and you can multiply it by a constant, right? And then you can add those terms up. And what you end up there is a linear differential equation. And it's linear because you're basically just multiplying a constant coefficient by the state terms or the derivatives or the integrals of the state terms, right? But you're not allowed to multiply the state terms together, and you can't say x squared. That's not allowed. That would not be linear. You can't say x of t times y of t. That would be nonlinear. And the coefficient cannot be a variable, right? It has to be a constant. But as long as you have basically just an equation of these state terms, signals, or derivatives or integrals of the signals multiplied by constants, it becomes a linear differential equation. So it's not linear in the sense that you plot it and it's a straight line. It's a linear differential equation, okay? And so basically that's the linear part. And the time invariant part just means the coefficients don't change with time. So the coefficients are, constants, right? Okay, and so LTIs have can have a frequency. You can calculate their frequency response. So usually you're concerned with hitting these things with or measuring the frequency response, which which generally will change the phase or the amplitude of a sinusoid, but they won't, create a new sinusoid out of nowhere, right? Okay, so here's an example one. So you can have an equation, and you don't even have to structure it this way. This is basically just saying u of t equals y of t plus the first derivative of y of t with respect to t minus 6 times the integral of yt dt, right? Now you don't have to. I just made this up, right? This could equal 0. Like you could move all terms to one side and have it equal 0. But this just describes the relationship between two state variables, u, or two signals, however you want to think of them, u and y, right? And so this could be a physics equation. This could be, this could come from a circuit, right? But it's just describing the relationship between these, right? There's no inputs or outputs here, really, not yet. It's just it's just an equation, right? And it's bound by the rules in this case of a linear time invariant, LTI, linear time invariant. However, you can choose a variable and call it an output. And you could choose another variable and call it the input. Okay, so at this point, we're taking this equation and we're saying, I want to conceptualize this as a box where I have an input and an output. Okay, so then I could say, well, let's say, and by the way, when I say input and output, I'm talking about a dependent and an independent variable, right? Now, this by itself doesn't define dependent and independent variables, but I can impose that. So I can say, well, how about if u is the output, y is the output and u is the input, right? And so if I do that, then I create what's called a transfer function, right? So I take this equation and I can convert it into a form that is a transfer function where y is my output and u is my input, or y is the dependent variable and u is the independent variable, right? Now again, these are variables, they're state variables, signals, time series variables, right? So now when you do that, one way to do it is to do it in the S domain, to do a Laplace transform. And a Laplace transform is very easy in this case. You just first of all, you take the variables and you make them capital instead of lowercase. Why is that important? I don't know. I don't know why that's a big deal, but you have to make them capital letters, right? And instead of being functions of t, they're now functions of S. So instead of time domain, they're going to be frequency domain, right? Okay, and then if you have a derivative in the time domain, you just have to multiply that variable by s. So this becomes, instead of derivative of y, it's just sy, right? And then if it's a second derivative, it would be s squared y. If it's a third derivative, it would be s the third times y. And then if it's an integral, it's 1 over s. Or if it's a second derivative, 1 over s squared. Or you could say s to the minus 1, right? And so this transformation is trivial, right? Easy, right? But then you have to restructure it using some algebra in order to make it a transfer function. In a transfer function, you want to express this equation as y of s over u of s. So you just have to use some algebra to basically factor out y and u so you can get them both on one side of the equation as a ratio. And then on the other side of the equation, you just have basically a ratio of two polynomials of s. That makes sense? So, so the way you would do that here is that you'd say you could factor out the y of s here, like here, and then you can divide both sides of the equation by u of s, and then divide both sides of the equation by 1 plus s minus 6s to the minus first power. Okay? And so that will give you this transfer function. And generally, when you do that, you want this ratio. So notice that there's only state variables on one side. And on the other side, there's only s's, right? But this is supposed to be a ratio of two polynomials. So you can generally, the case that this denominator, you want this to be a polynomial where the lowest power of s is 0, right? So you'd multiply this thing by s over s to get it into the right form, right? You don't have to, but that's I didn't do it there, but yeah. So anyway, you have this, this ratio, right? Now you might be thinking, wait a minute, that's fine, but, and we're going to use this as a model for a plant and a model for a controller, assuming that the plant can be modeled as, you know, we could pretend it's linear, right? The problem, though, is you might be thinking, well, what about if I have more than one input and output? That's a problem, right? Because this is kind of, your description of this is pretty much limited to one input and one output, right? Yes, yeah, that's, with S domain, you can do multiple input, multiple output, but then you end up having to express the transfer function as a matrix, right? Which gets tricky, right? So in this class, in this crash course, I'm just going to show one input, one output, just because I only want to spend, you know, like 2 lectures on this, right? So just keep that in mind. One input, one output, but it is possible to scale this up by using us, you know, by converting this to matrix form. Okay, now the nice thing about transfer functions is, the reason why people like transfer functions is that they're composable, meaning that you can take a transfer function and you can feed the output of one transfer function into the input of another transfer function by simply just multiplying them together. And it works out because, for example, and the notation is a little weird here. Like, so I have a transfer, notice this is starting to look like a block diagram, by the way, because that's generally how these are designed. Like if you go into Simulink and MATLAB, which is the most common tool for designing these LTIs, it's literally a block diagram. It just starts to look like a circuit design thing at this point, right? But what you're doing is you're creating these blocks. Each one of them is a transfer function. And so this one's labeled Y, but what that means is its output is Y. Okay, its input here is U. And so its transfer function is actually Y of S over U of S. But generally, people do a shorthand on these things. So they'll just say Y. A lot of times they kind of drop the fraction, but it's really Y of S over U of S. And then you can have another guy, G, which is named G because its output is G, but its input is Y. And it's really just G of S over Y of S. And if you want to take these guys and ram them together, you know, merge them together, connect the output of this guy into the input of this guy, you just have to multiply, in which case the Y is the internal wire, the internal connection. It actually disappears, and it actually, you know, it'll factor out in the math, right? Because you'll have a Y of S in the numerator and denominator, so it goes away. And so essentially when you merge these two guys together, this Y of S kind of disappears because it gets lost in the abstraction, right, of the combined system, right? So this ends up being, this combined thing is G of S over U of S, right? Makes sense? And all you have to do is multiply. When you multiply two transfer functions, that's called a convolution. And it's basically just algebra, right? You're just literally just multiplying two ratios of polynomials together of S, right? Okay, so then there's this other concept called stability. So a transfer function can be stable or unstable. Or more specifically, it can have bounded input, bounded output stability, which means that if it's stable, no matter what input I give it, it'll produce a bounded output, right? You might say, as opposed to what? As opposed to if I give it the wrong frequency input, it blows up into infinity, right? That's an unstable system. Now you might say, wait a minute, how can that ever happen though? It's impossible. That would violate, like you can't have like a system, like you're talking about these things are supposed to represent physical systems, like an object. You're telling me that you can create an object and you put an input into it and it generates an infinite amount of energy by blowing up. Seems impossible, right? Yes, it is impossible for physical objects, because the reason why is because in real life, there's some kind of damper going on that dissipates energy. There's always an energy dissipating element in every physical system. So physical systems cannot be unstable. However, our objective is to create a controller, right? A controller isn't a physical thing. A controller is it's code, basically, right? So what your goal is to be able to take a controller, which is a transfer function, and hook it up to a plant, which is a transfer function, convolve them together, right? And then you create another transfer function. And you're hoping that the combined transfer function is stable, because you don't want the combination of controller and plant to go crazy in response to certain situations, right? You want it to be bounded, right? Now you might say, well, come on, even code has to be, can't blow up into infinity. I mean, if you have a controller and it has an output signal, that signal is associated with the numerical value, which is stored in a register, and that register will saturate at some point. It'll go out of bounds, right? It doesn't, no computer can store a value that has infinite dynamic range, right? True, but it will eventually, get to that point. It'll peak out and die, right? If you have a bad so in other words, what I'm trying to say is you could create a controller system that could give you an unstable system or a controller system that gives you a stable system. You want, at the very least, your controller should be stable. Does it make, the combination of the controller and the plant should be stable. Does that make sense? Okay, so that's the idea. So, so how do you know if a system is stable? There's lots of ways. There's three that I know of. The first way is if you have a simulator that can simulate a system like this, which is generally MATLAB is essentially the only one, I think, the only widely used simulator for this. You can hit your transfer function with an impulse. An impulse is basically when the input is 1 at time 0 and 0 everywhere else. Right? It's like it's equivalent to taking a hammer and whacking something as hard as you can, right? That's an impulse, right? And the reason people use that is because there's two reasons. One, it has a very simple Laplace transform. The Laplace transform of an impulse is 1, right, in the S domain. But the other reason is that an impulse contains an infinite number of frequencies, right? It's basically saying, I'm going to hit you, because in order to add up sinusoids to create an impulse, you have to add up an infinite number of sinusoids to get an impulse, right? As you would also a step function, which is where you go from 0 to 1, right? So if there's any frequencies in there that cause a blow up, instability, you'll see it. So you just take your system, and I think in practice, this is what most people do in practice. They just take it and they hit it with an impulse in the simulator and they see if it blows up, right? They look at the impulse response, right? That's one way to do it. But I don't want to turn this into a MATLAB course, so we're not going to be able to do that. Another way to do it is you could do it mathematically. If you have the transfer function, remember that the transfer function is a ratio of two polynomials, right? It's two polynomials. There are values of S that will make the denominator 0, and you'll get a divide by 0. It's undefined, right? Those values of S that cause that are called poles, okay? And so you can solve the poles. You can find out what the poles are. Now S, by the way, is an imaginary number. It has a real component and an imaginary component, right? If the real component, forget about the imaginary component, but if the real component of all the poles is negative, okay, which means that if you were to plot the poles on a two-dimensional axis where the vertical was the imaginary part and the horizontal was the real part, if all the real parts of the poles were negative, all those poles would be on the right-hand side of the plot, right? It would be less than 0. It would be to the right of the vertical axis. If they're all there, then it's stable. But if even one pole is either has a real component that's 0 or a positive real component, the system's unstable, right? So that's another way to find out if it's stable. And then, finally, the other part is you can do an inverse Laplace transform. You could take it from S domain back to time domain. Once it's in time domain, hey, then I can just plot it. I know exactly what's going on. But how do you do that, right? That's the problem. Well, that's kind of tricky. So I already talked about that, sorry. Okay, so if you have a transfer function, for example, this, so we have S over S plus S squared minus 6, and I should put that in the right order. Should be s squared plus s minus 6. So I got a transfer function here. So I want to do an inverse Laplace transform of this, right? Can I do that? I want to go from going from time domain, like if you have an LTI and you're going from time domain to the S domain, that's easy. But going back to time domain, that's the problem. How do you do that? Well, it's really hard. So generally speaking, the way it's done is use a table. There's a table. Someone figured out this table. And the table has a column of time domain on one side in one column and Laplace domain in the other column, right? And your goal is you got to take your equation, your transfer function, and you have to get it into a form that matches something in the table, right? And then you just look it up. You might say, that's kind of brain dead. Yeah, it's awkward. No one does this, by the way, but this is just one way you can do it. So notice in the table, there's something that says 1 over s minus a, and that transforms into e raised to the at power, right? So if I can get it into this form, I can do that transformation. So the way you do that here is I'm going to factor the denominator. So this is going to be s over s plus 3 times s minus 2. Now, by the way, I could tell already that the poles, I got a negative real pole and a positive real pole. So this is, I already know it's unstable, right? But now I just want to prove it's unstable by the inverse Laplace transform. So I got to get this into that form. It's not in that form. So I'm kind of dead in the water already, right? Unless I can take this expression and break it up, decompose it into terms that are basically some constant over s minus some constant, right? So can you do that? Well, basically, no. You can't. I mean, sometimes you can. In this case, I can. Usually, you can't. I can do it in this case because both poles are unique, right? So the way you do it is you basically say, well, I want to convert this form into that form. So I got to basically solve for a and b, right? No problem. One equation, two unknowns. I can do that, right? Probably not. I don't think you can do that. I think you need two equations and two unknowns if you want to solve. This is underdetermined. But you can do it. There's a hack. You can hack this to make it work. The way you hack it is you re-express it. So you take this form and you put it back. You take this form and you make the denominator s plus 3 times s minus 2 again, but you do it by essentially forming a common denominator here, right? And then multiplying b times s plus 3 and a times s minus 2, right? So you get this form, right? Okay? So then, once I have it in this form, I can cancel out the two denominators on both sides, right? Which gives me s equals a times s minus 2 plus b times s plus 3. Okay? Now you might be thinking like, okay, still not helping. It's still one equation, two unknowns. You can't solve this. It's impossible. Well, what you can do is you can imagine that s just happens to equal 2. If s equals 2, then you'll have 2 minus 2 here, right? Now that'll knock out that whole term and the unknown variable a, right? But then I'll have 2 for this s and I'll have 2 for this s, and then I'll have one equation with one unknown, and I can solve for b at least, right? Right? So I can do that, and I can do the same thing for a. I can set s to be minus 3, right? Minus 3, right? If s is minus 3, then it'll essentially delete b, and I'll just be left with a and a, and one equation, one unknown. So I can solve for those two that way, and then I'll get my solution, which is a is 3/5 and b is 2/5. So now I have the original equation in this form, which now I can look up in this stupid Laplace table and do an inverse transform. So basically, the idea is that I need a and t. A is this number here, right? right? And then whatever's in the numerator will just be a coefficient, right? So this can then be converted into time domain. It ends up being 3/5, right? 0.6 e to the to e raised to the negative 3t power plus 0.4 e raised to the 2t power, right? So this becomes the time domain. Now you might say, wait a minute, well, time domain of what though? Like what is this giving you? What is this exactly? Well, this is actually the time domain representation of the transfer function. Remember, we started with the transfer function, right? Well, you might say, okay, that's fine. That gives you the time. This is the amplitude versus time. Where's the input? How's the input factor into this? I got to give, the whole point is, if I give it the wrong input, it blows up, right? But there's no input in this, the inverse Laplace. It's just t, right? How do you figure this out? Well, it's the transfer function. Remember I said that the impulse, the S domain of an impulse is 1. And I also said that if you multiply, you multiply two transfer functions, because the transfer function of an impulse response has no input. It's just 1, right? There's no, right? So basically, what you end up with when you do this is the impulse response, essentially. It is what you would get. This is this, if you plot this relative to time, it's the same thing you'd get if I hit the impulse, if I hit the transfer function with an impulse, right? Now, obviously, you can tell already that this guy is, this term is a problem, right? Because 0.4 e to the 2t is not bounded. It's going to blow up, right? And so then if I plot this, okay, you can see that, it's just an exponential function. It looks like any other exponential function. It just goes off into infinity. But this is the same thing you would get in MATLAB if you built that S-domain transfer function and hit it with an impulse, right? You'd get this. Unfortunately, I never figured out how to do that. So I never got the impulse to work in MATLAB and Simulink. So instead, I just use a step function because there's no, I never found the block. I just use step functions very similar to impulse. In fact, the S domain of a step is just 1 over S. So I simulated this in MATLAB. So I took the transfer function, I stuck it in Simulink, I hit it with a step, right? And when you hit it with a step, it doesn't just go up like an exponential. You get this weird oscillating effect, but eventually the oscillating effect just blows up into infinity, right? So this is unstable using the poles method, it's unstable using the inverse Laplace transform, and it's unstable using good old Simulink. By the way, these are called eigenfunctions. When you do this trick, these things are called eigenfunctions, these exponential, sum of exponentials. Here I hit it. I decided to hit a couple other things too with this. Instead of just a impulse or step, what happens if I give a sinusoidal input? And, how about 2 radians per second? Just make up enough frequency. Hit it with that and it blows up. Now again, this is blowing up mathematically, assuming that it's a linear system in real life. There's limits. This won't, it's like in real life, if you had, you can't build something that's unstable and then hit it with an impulse and have it destroy the universe, right? Because it's not going to work. It's not going to happen. Okay. So what happens then? Let's just quick example. What happens if the poles were negative? I mean, the real component was negative. Let's say my poles were over here on the negative side, right? So all I have to do is I can hack this, and I could change my transfer function and force it to have negative poles. I could force it. All I had to do is change the sign of one of these two guys, right? So I go through the same steps. I calculate my eigenfunctions. And what I end up with here is my eigenfunctions end up having a negative exponent on the exponentials, right? Just by changing the original sign up here in the S domain. And when you do that, you get this, first of all, it sort of asymptotes here to 0, right? But it overshoots 0, right? So I hit it with an impulse, it goes down, and then it comes up. Kind of strange. But yeah, but it's stable, right? Because it stabilizes at 0, right? Not sure what that glitch is at the beginning, but it stabilizes, right? So then I'll do the same thing in MATLAB. I'll hit it with a step function. And the step function gives me a similar type of response to the impulse. Kind of goes up, and then it comes back down, right? And of course, I know the poles are negative, so it should be stable, right? And now, just for completeness, I'll hit it with a sine wave. And the sine wave, you'll notice that something odd here happens here. The sine wave changes magnitude, so there's a gain, or an attenuation, I should say. And looks like there's a phase shift, because that sinusoid doesn't, there's like a little glitch there at the beginning. Unclear if it changed the phase or if that's just an artifact of the plot. Okay, so if we want to convert, let's say we want to convert a physical system to a transfer function, how do you do that? Well, here's a really simple example. Okay, let's say I have a coin. Let's say I want to program a robotic finger to move a coin, like just to drag a coin across the ground, right? And so let's say that I can program the robotic arm to put a certain force on the coin, in newtons, right? And so that's my U, that's my input. And then the coin is going to have basically an output, which is Y. That's where the coin's going to go when it pushes. The robot pushes the coin with a force, and the coin ends up somewhere. So you can model that as a linear system by saying U minus B, which is the coefficient of friction. B is how much resistance you have as you drag the coin across the ground. Now, in the case, the way friction works, you guys probably remember this from physics, the amount of force I get from friction is proportional to the velocity. So the faster you rake the coin across the ground, the more resistance you're going to get due to the friction. So I'm going to represent that as basically y is the position, right? The derivative of y, is the velocity, right? And I'll represent that as y dot. So this is just another notation. This is the lazy man's notation. Instead of saying dy dt, actually, instead of saying dy of t dt, you do this super lazy thing that everyone that does this stuff uses, this super lazy y dot. No t, no d's. That just represents the first derivative of y with respect to t. Okay, now, so I've got an input force and I've got a resistive force. So I'm going to subtract. And those need to equal the total force on the coin, which is, mass times acceleration. So it's the mass of the coin times the second derivative of y, right? So they have to equal. Now you can see that this is just relating the terms, right? This equation by itself, again, is not assigning anything an input or an output. It's just saying, look, these things, they have to equal out, right? But if I design this as a transfer function, then I can say, well, u is my input and y is my output. This is now the control system part of this, is where you conceptualize this as the transfer function. So you can just essentially convert this to Laplace domain. So the y dot obviously is sy, and the y double dot is s squared y. And you got to use the capital letters though. You got to go capital, because that's important, right? You got to go capitals on these when you go Laplace. And then, so now I've got capital U and y, and you end up with a transfer function of y versus u of 1 over ms squared plus bs, okay? So I will factor out s. I'm going to factor out s. And so I get s times s plus b over m, and that's a problem. That's a problem, because that is not, is that stable? Probably not, right? Because there's two poles. One of them is 0. Well, 0 is not a good pole to have. The other one's negative b over m, right? That one's okay. So that's a problem. That's a problem. So is that true? So let's say I put that in MATLAB and Simulink, and I simulate it with a step. Yeah, it is actually unstable, believe it or not. It's, despite what I said earlier. Because if you give it a step function, that's basically like saying, I'm going to set the force to 1. I'm going to give it a constant 1 Newton force and leave it there, and then the coin will just, yeah, it'll zip off into infinity. So that's unstable, right? Let's look at another one. Here's a better example. This is called a spring mass system. So if you have, say you have the ceiling, you attach a spring to your ceiling and you attach a mass to it, okay? And so this thing just kind of dangles, right? You have an x. X is the position of the mass, right? Now, this x is, you think of this as having a 0 point here, right? So what ends up happening is that if this x becomes negative, like if I push up on the spring, what's the spring going to do? It's going to try to extend. It's going to put a force, an opposite force, right? But likewise, if I take this mass and I pull it down and x is positive, spring's going to want to now contract, right? Right? So either the spring is going to be pushing out or it's going to be contracting, depending essentially on the sign of x, right? And so the force that it has in doing that is called the stiffness K, right? There's a constant there. Now this ends up, you can model this as a linear system. Now you might say, now wait a minute though. It is a linear system, right? Well, no, in real life it's not linear because springs have limits. If I take this guy and I push it up, eventually that spring is going to get to the point where you can't compress it anymore. It's going to turn into a solid block of metal, right? Likewise, if I stretch the string out really, really far, at some point it's just going to break, right? Those are the nonlinearities. But if I just assume that, yeah, the spring has infinite flexibility, then it's a linear system. Okay, so I can describe this in almost the same way as I did the other one. Basically, U of t, which is the force that I'm pushing down on the mass, and I'm going to subtract the spring constant times the position, right? So springs, remember before, I had a friction on there that was relative to the velocity that I was moving the coin. But in this case, the spring is going to exert its force just not based on velocity, just based on how much I'm stretching it. Very simple. So I don't even have to take the derivative. It's just K of t, right? K times x, okay? But both of these together, now, by the way, this is negative because, again, if I go up, right, if this is negative, if K of t is negative, spring is going to be going out. If I pull it down, the spring is going to be going up, right? So this is negative relative to the force I put in, right? And then these both have to equal the total force of the mass, which again is just mass times acceleration, right? So I can take this, I can do the Laplace transform again, and then I can construct a transfer function. And again, this transfer function like is up to you, like because my input could be the spring stretchy, right? And then I could be using the position of the mass as the output, or my input can be the mass and the output can be the position, right? You can set this up in different ways, but in this case, I'm assuming that I'm grabbing this mass and I'm doing something to it, right? Okay, so it's going to be, what is it? It's the output is x and the input is u, right? So it's x over u, I think. Yes, x over u. And now I have a transfer function which actually looks a lot like the other transfer function that I had. And now, once again, I got some bad news, is that I left m and k as variables. The poles here are, well, the good news is I finally have an imaginary pole. That's the good news. You can't have imaginary poles. The bad news is that the real portion is 0, right? So that's no good. What ends up happening here is that in this case, what I've calculated with this pole is actually the natural frequency, the resonant frequency, which turns out to be the square root of k over m in radians per second, not hertz. You can convert to hertz just by dividing by 2 pi. Right, this is the resonant frequency, okay? Which means what ends up happening with this is the reason it's unstable is because if I take this guy and I start putting an input, this k, u input, sorry. If my u input matches the resonant frequency, this thing will start oscillating bigger and bigger. You can think of it like, a better way to demonstrate this is if I had a bar and the spring was attached to the bar and I had the weight, and I start going like this, and things started bouncing and bouncing. And if I get the right frequency, it'll get bigger and bigger and bigger, right? Of course, it'll eventually break the spring. But that's the natural frequency. This is unstable, right? Now, in reality, what ends up happening in real life is that you also have this damping. You have a damper, right? Because that spring, whenever you stretch out a spring, it actually heats it up. It actually stores energy in that spring. It'll actually heat. If you take a spring and you go like this, and it actually heats the spring up, right? And so that heating effect is essentially a damper, right? And so you have this hidden damper. And so what ends up happening is that you have to add a damper term. So the damper is a third term on the left-hand side of this equation, and the damper ratio, the constant, is B. And basically that is also a negative term, but the dampering is relative to the velocity, right? So it's equivalent to the friction of the coin dragging across the ground like I showed in the previous example. And so when you add that damper term and you solve it, you actually end up with another transfer function. And in this case, the poles are all negative. Just by adding that damper, you end up with negative poles. So it becomes stable. It's a stable system. So anyway, just as an example, I can put values in for m and k. So m can be 4, k could be 1, and then I can calculate the natural frequency of the system. But anyway, okay. But you can still get the natural frequency, but it's stable. Okay, so one last example. Here's a circuit example, just to show that a lot of these are equivalent. So if I have a voltage source and I have an inductor and a capacitor, this is an LC circuit, right? No resistor, though. I did that on purpose, right? So there's no resistor here. And you can calculate, you just do an S domain of the mesh analysis, the voltage around the circuit, right? So you have LSI plus 1 over CS, where I is the current and V is the voltage. And so you can calculate a transfer function with that the same way. And you end up with poles that, again, are both have a zero real component. They have a zero real component. So they're unstable, but you end up with your resonant frequency, which is the square root of 1 over RC, right? So this thing will blow up if you hit it with square root of 1 over RC radians per second input on the voltage, right? But again, just like with the spring mass system, all you got to do to fix that is if you add a resistor in there, right? That resistor will dissipate the energy and it will prevent it from being unstable. And so you do the same thing and you end up with poles that are strictly negative in terms of the real part. Okay, so that's transfer functions. So how about the controller? Then how do you build a controller? So we talked about closed loop control, and we talked about how you can combine transfer functions, you can convolve them, you can merge them together. So if you have a plant, so this is the plant transfer function, and I'm going to create a controller transfer function, right? And I'm basically going to feed the controller into the plant, okay? Now I'm done. Of course, that's just an open loop controller. If I want to close the loop, then I got to come back around and I got to subtract the process variable with the set point, which I call rref, right? And that will be the input to the GC. So the question here is, how do I figure this out? Like how do you solve this? Because if I have an output of one guy and do an input of another one, I just multiply them, but now I got a cycle. I got a circle. How do I figure this out? So it's not that bad. You have to kind of figure out, you have to solve this though, algebraically. So if we call the output of the plant, the process variable, we'll call that the closed loop Y. I don't know what Y stands for. Like Y is, it's like whatever's going on, whatever the plant's doing. It's like the altitude that the drone's flying, whatever you're trying to control. That's Y closed loop, right? And then, so Y closed loop is obviously going to be GC controller transfer function times the plant transfer function, right? But I've got a third transfer function, which is this error term, right? So the error term is Rref minus YCl. Now these are all still S domain. I didn't put of S because I was lazy. And I didn't represent these transfer functions as fractions, even though they are fractions, because I was lazy. I just named each one of these as uppercase output, right? But these are all of S, and they're all ratios of two things of S, right? Okay, so just keep that in mind. So this is the simplified closed loop, right? Okay, but the problem is that I don't want it in that form though, right? What I want is my input to be Rref, and my output should be Y, right? So it should be Y over Rref of S, right? That's the wrong form. I got to get it into the right, that's meaningless, right? I got to get it in the right form. So you can just do some, you do some algebra here. So you multiply these guys out, and then move one of the terms to the other side of the equation. Okay, then you factor out YCl. Okay, now again, our goal is to get it to be YCl over R, because remember, numerator is output, denominator is input. So if I want the closed loop response of this whole thing, I need YCl over R, I gotta get it in the right form. It's gotta be output over input, right? So, yeah, basically I just go through 3 steps, I can get it there. Well, not exactly, I still need to get Rref out of there. There we go. Okay, so I divided both sides by Rref. So now I have YCl over Rref is GP times GC over 1 plus GP times GC, right? It turns out that this result is significant because GP-GC is the open loop response, right? And the closed loop response is simply the open loop response divided by 1 plus the open loop response, which is kind of crazy it works out that way, but it's that simple. That's the only thing you have to do to convert open loop response to closed loop response. Okay, so how do you design the controller? Well, this part I think you guys already know. Or one way, the simplest way, is the PID controller, right? The proportional integral derivative. You guys did this in robotics, right? 274. But I don't think they covered any of the background of why this works, right? So basically, you have 3 tuning variables. You have a coefficient for the proportional control, a coefficient for the derivative, and the coefficient of the integral, right? And so basically, you choose these guys, and you get a differential equation that looks like this. You have the error term, which in this case I have error. This is time domain. It's in the time domain. In the time domain, I multiply the error by a factor, right? I multiply the derivative of the first derivative of the error by a factor, and I multiply the integral by a factor, right? And the result of that is the output of the controller, right? This is just the controller block, right? Okay, so in the S domain, I can convert that to S domain. Right, so I convert it to S domain, except I don't have the E in there. It should be G over E, right? Okay, but then I end up with something that looks like this, right? So unstable by itself anyway, right? It's got a 0 pole, but I have it in this form now where it's a ratio of polynomials of S, and now all I got to do is to calculate the open loop response, just multiply it against the plant transfer function, right? Okay, but the problem is that let's see. Yeah, you can also just drop you can drop the derivative. In this case, I just have a PI controller. So in order to simplify this, I'm just going to use a PI controller. I'm going to drop the derivative term because otherwise it gets cumbersome when you work it out anyway. Okay, so here's my here's my controller, my control system. Okay, so now this first term, I'm going to calculate the open loop response. So that's basically that times that. Transfer function of the controller times transfer function of the plant. The transfer function of the controller, if it's just a PI controller, no D, is the proportional control times S plus the integral control divided by S, right? And then the plant is my robot moving the coin plant. This is the coin example, right? So I have B, which is the friction of the floor that I'm raking the coin against, and M is the mass of the coin, and that transfer function is 1 over M times S plus B over M, okay? Now the problem with this is you might say, well, that looks great, but how do I pick the values? How do I pick the values of K and P? Well, that's the tricky part. How do you do that? I'll set M to 1 and B to 1 for simplicity. Okay, so when I multiply these two guys together, I get an open loop response, K times S plus K of I over S squared plus S plus 1. But remember, this is the open loop. This is not the closed loop. This is the open loop response. If I want the closed loop response, well, here's where things get a little bit more complicated. Now, I have to take the open loop response and put it in the numerator and then say 1 plus the open loop response is the denominator. Now I have the closed loop response, right? So now I got to figure out if this is stable. Well, that sucks. That's just terrible. So you got to kind of work it out. Okay, so I worked it out. If I simplify this, I can get a ratio KPS plus KI over S squared plus S to the third power. Now there's 3 roots of this thing now. S3 plus S2 plus KPS plus KI. Now I have to pick values of KP and KI. So how do you do that? Well, how does most people do that? They just randomly pick values, basically, right? MATLAB has something called a PID tuner. I have no idea how it works, or if it works. However, I found a really cheesy way to do it. So I just want to guarantee this is stable for the moment. I don't want this to blow up, right? I want it to be a stable controller. So all I need to do is guarantee that the roots are negative, have negative real parts. So I'll take the denominator here, and I will assume that I want it into a form of S plus A. I want to be able to factor this into S plus A plus S plus B plus times, I'm sorry, S plus A times S plus B times S plus C. I want A, B, and C to be positive. Because as long as A, B, and C are positive, that means all 3 of my roots are negative. And then I'm stable, I'm good. Mission accomplished, right? The problem is that I need to figure out, I need to figure it out how it relates to this denominator. So if you have this guy and you multiply this out, it's going to be S cubed plus ABC times S squared plus AB plus AC plus BC times S times ABC, right? That's just the expanded form of that guy. And then I can say, if I compare this expression to this expression, I can see that A plus B plus C, which is the coefficient of the S squared term, it's got to be 1, right? Because it was 1 here, right? Likewise, AB plus AC plus BC must be K sub P, right? And ABC has to be KI. Make sense? So as long as I pick a KP and a KI that's constrained in this way, then I should have a stable system. So I picked 3 values that work out. A is 0.25, B is 0.25, C is 0.5, and then I went back and I calculated the K and the KP and KI from that, and then I now have my controller, and I put this in MATLAB, and I hit it with a step response, and looks good, right? Actually, this is the impulse response. I guess I did figure out how to do the impulse response when I generated these, right? So this is the impulse response. I want the step response, though. There's the step response. Yeah, sorry. That's the impulse. There's step. So here's the step response. So basically what this is saying is, now remember what this represents. the step response is assuming that what is the input? The reference, right? So the reference is where I want the thing to be, right? So this is like saying, robot, move the coin 1 meter. Actually, move it 0 meters, but then I'm suddenly going to change my mind and say, move it 1 meter, right? That's what the step response is. The output, the response, is where the coin actually is, right? So what's happening here is that the robot, I'm telling the robot, don't move the coin. All right, move it 1 meter. And the robot is moving it up very slowly, but then he overshoots. And he's like, oh, sorry, and he has to go back, right? So the robot moved it, and he said, he had a little bit too much gusto. Moved it too far, right? And then he had to correct himself, right? So that's called the overshoot. He overshot. And this is called the rise time, how fast he got it to the set point. So as it turns out, what I said earlier wasn't entirely true. I said, the only thing I care about is that the controller and the plant together are stable. I said, that's all I care about. But in reality, I also care about this overshoot and rise, right? Because I don't want the robot to have too much gusto. Plus, I want it to get the coin to the set point faster, right? That's kind of like the performance of the, yeah, it has to be stable. If I pick really bad parameters, I think I could have made it unstable. I haven't tried that. I think if I choose really bad K and KP, KI, I could probably unstabilize this thing, maybe. I don't know if that works out mathematically or not. But certainly I can do better with this, right? So I'm going to fix some stuff here. I can increase KP. I'll increase the proportional response, which gets me a better rise time, but a worse overshoot. Not only that, but it oscillates here, right? Or I can increase the integral term, which increases the overshoot for some reason, right? So that's no good. But basically, it's just trial and error, right? Okay, so, and notice, this is kind of cool too. One thing that they don't usually show on the step response, remember that the blue line is where I'm telling the robot to push it. The yellow line is where the coin actually is. But what I didn't show was the actual force the robot put on it, right? Because that was hidden, right? That term is actually this guy. It's in the middle of, it's between the controller and the plant. Usually you don't see that, right? Because it's embedded. But I can call that out. I called it out, and this is the actual force that the robot put on is the orange line. You can actually see what the robot's doing there, right? Okay, so I gave it you can give it a sinusoid. You can like, robot, push it up and bring it back, push it up and bring it back, push it up and bring it back. And then you can see how well the robot responds to that. Okay, but anyway, so that's the PID controller. Okay, so now the problem is, there's another problem. The problem is that it's impossible to design a controller that does that. Can't be done. Because what I've just showed you is a continuous controller. And we don't have any continuous controllers. They don't exist. Well, they do exist. People have done things like they have a greenhouse, and you want to control the temperature in the greenhouse, and you control it by making the vents out of a metal that expands when they heat up. So when it heats up in the greenhouse, the metal expands and it closes the vents, or opens the vents, rather. Right? That's a continuous controller, but that's not computer-based. It's a piece of crappy metal, right? What if I want to build a computer that does that control? It can't be done. You can't design an S-domain controller. It's impossible. That's continuous. Computers are discrete. So there's a big problem there. So what do you do? Well, there's a few ways to deal with that. One way to do it is using the Z-domain instead of the S-domain. The Z-domain is the equivalent of the S-domain, but for a discrete controller. Okay? So basically, it's similar. You start out with a time series signal, which is sampled at uniform sample points. So instead of x of t, you have like x of n, where n is the sample, not time, but the sample number, right? And usually you got to use brackets for that because Can't use parentheses if it's discrete. That's not allowed. You got to use the brackets. Parentheses are only for continuous systems. But sometimes I still make that mistake. Okay, so what ends up happening is that in a discrete controller, you have this continuous signal, but because everything happens at discrete points, the computer updates at discrete times, you end up doing you digitize, you create like a Nintendo type step pattern, right, that follows the discrete signal, right, or the continuous signal, right? Okay, so basically the idea here is that you start with a time domain, but it's not continuous time domain, it's discrete time domain. So you got the brackets in there, bracket T, bracket K, not parenthesis. You can convert the time domain to a Z domain through Laplace transform? No, I don't know, Z transform. They don't have a fancy French name for it. It's just called the Z transform. No one takes credit for the Z transform. They don't have a Laplace. Also, instead of a differential equation, it's not called a differential equation anymore, the time domain. It's called a difference equation because a differential equation is only for continuous. Okay, so then you convert it to Z domain, and then you can calculate the transfer function in the Z domain. However, the stability test is completely screwed up in the Z domain. See, in the S domain, you can tell if a system is stable or a transfer function is stable. You just look for the roots, the poles, the roots of the roots of the denominator polynomial, right? And as long as the real component is negative on all the poles, no problemo. Z doesn't work that way. In fact, the Z rules for stability are totally arbitrary. A system with poles that are close to the origin, 0, 0, 0, just 0. It's a complex number, 0. If you're close, the system will settle rapidly, right? Meaning that you hit it with an impulse and it'll settle rapidly. A system with poles that are close to the unit circle around the origin, it'll settle, but slowly. What's rapidly and slowly mean? Unclear. That's unclear what that means. Very flaky, right? A system with poles right on the unit circle, they may have a sustained response. Or they may blow up to infinity, catastrophically. Unclear. That's if they're on the unit circle, right, the poles. And a systems with poles outside the unit circle, well, then definitely you're screwed, right? Okay, so the rules here are different. Okay, so here's an example. If we go back to the original made-up differential equation, continuous, you go from continuous to S domain, time domain to S domain continuous. And if you have a discrete system, so in this case, how am I representing the derivative here? Y of k, that's the value at the current time. The derivative is the difference between the current and the previous sample, right? That's the slope. And then the integral is the summation of all the values I've seen since time equals 0, right? So I use a summation instead of an integral sign because it's discrete, right? And then I can transfer this to Z domain. So once again, I got to go uppercase letter. But instead of S, it's Z, right? Now, the derivative, this part's wild. The derivative is not replaced. What is it? Normally, the derivative in the S domain is just S, right? But in the Z domain, it's not just Z. It's Z minus 1 over Z. Why? Why? Why would they do that? Well, I'll explain that. It actually does make sense. This one is the integral, or it's not really the integral, it's the summation, is actually Z over Z minus 1. So instead of, remember over here, the integral was 1 over S. Over here, it's Z over Z minus 1 is the integral. Okay? So why? And then you can calculate the transfer function the same way in the Z domain. Okay, so what is going on here? Okay, let me talk about this in a second. So the derivative is Z minus 1 over Z. Why? Why is that? Well, you can take that and you can take this, it's equivalent to z over z minus 1 over z, right? Which is 1 over z to the minus 1 power, right? What does that mean? What it means is that z to the minus 1 power simply represents the previous sample. That's all it means. So in Verilog, if you have a register that causes a 1 cycle delay between its input and the output, z minus 1 just means register, right? Essentially what it means. And 1 is the current value. So z to the 0th power is whatever the current sample is. Z to the minus 1st power is whatever the previous sample was. And z to the minus 10th power is the 10th 10 samples ago into the past. So if you had a shift register with 10 elements, that would just be whatever's coming out of the shift register at the end, right? That makes sense, right? Right? But what about the integral, though? How does this become the integral, z over z minus 1? How does that work? Well, this one's kind of crazy. So if I use some long division here, if I take z minus 1 and divide it by z, okay, using some long division, I can get 1, right? But then I have to subtract z minus 1 from here, right, to calculate the remainder, right? Okay, so I end up with a remainder of 1, right? But the remainder, remember, the remainder is over the original denominator. So now I have 1, right, with the remainder of 1 over the original denominator, which is z minus 1. Well, I have to keep going with this, right? I can take z minus 1, I can divide that into 1, right? So I'll do that. So z minus 1 divided by 1 is z to the minus 1st power with the remainder of z to the minus 1st power, right? So now I have, so that's equal to z to the minus 1st over the remainder divided by the original denominator, which is z to the minus 1, right? Then I can do it again, work out this fraction, right? Z to the minus 1 divided into z to the minus 1, or z minus 1 divided into z minus 1. And I end up with z to the minus 2 plus z to the minus 2 over z minus 1, right? Now, as you can probably tell, this is going to go infinitely, right? But what it works out to be in the end, I can keep doing this. What it ends up becoming is 1, the current sample, plus the previous sample, plus the previous sample, plus the previous sample, infinitely. This ends up becoming the summation thing, right? Adding all the samples up back to 0, right? So basically, when I showed the summation thing, right, for the time domain, that summation was actually mathematically equivalent to z over z minus 1. That's just the summation of all the current sample and all the previous samples, right? Assuming, of course, that z to the minus n means the sample n samples ago, or the value n samples ago, right? You got to take my word for that one. Okay, so at 3 minutes, I get one more thing I'm going to talk about, and then I'll tie this up next lecture. Okay, so how do we go then from what if we have an S domain transfer function? Because remember, when you do a physics equation, there's no Newton's laws of motion for discrete. They don't exist. Newton wasn't a computer scientist. Right, so all his laws are in continuous. They're defined continuously. So if I have a controller that I build in the S domain, because the plan's in the S domain, it has to be, right? The plan is an S domain, the controller is an S domain, I build my controller, I convolve them, but now I have to run this on a computer. But you know what the most important question is? What's the most important question is not can I run it, but what is the time, how fast does the computer got to be, basically, right? How fast, because obviously, if you have a physics equation that has high dynamics, right? Like moving a coin is low dynamics, right? But if I'm trying to control something in an explosion, that's fast, right? I'm going to need a computer if I'm trying to actively control something in an explosion or at hypersonic speed or whatever. I need a computer that keeps up. So the real question is not how you go from S domain to Z domain. The real question is, what is the sampling rate, the sample period, right? That's the real question. Because it may be the case that I can design a great PID controller that works great in the S domain, but it will never work in the Z domain unless I got it running on a fast computer, right? So how do we figure that out? Well, you can do a conversion between S domain and Z domain. This is pretty cool. There's various ways to do that, but the best way to do it is the Tustin transform. The Tustin transform is when you replace S in your S domain with a Z domain. You just don't make SZ. That doesn't work. You have to make S 2 over the sample time times Z minus 1 over Z plus 1. You back substitute this into S, and you will have converted your S domain into a Z domain, right? But you've introduced another variable, T sub S. That's the sample time, right? And so you can do all your stability measurements that way. So here's the physical model of the coin, and that's the Z domain of the coin, right? Now check this out real quick. So this is not the controller. This is just the coin model. This is the plant, not the controller. Okay? I converted it to the Z domain using the Tustin transform, and I had to do lots and lots of math. Lots and lots of math. This was awful. This is really awful. It's terrible. It's why people use MATLAB, I think. But anyway, I did all that. Oh, by the way, I picked a time. My time step was 1 second. Sorry, I forgot to mention that. 1 second time step, right? Every second there's a sample. I did all that, and I got the following transfer function, right? Now I can calculate the poles, the Z domain poles. 1 1/3. Unclear. Probably stable because they're inside the unit circle according to the rules, but unclear. So I'll simulate this guy in. Okay, well anyway, I have to. You can. I'll come back to that in the next lecture. But basically, I simulated this, and you can see essentially what happens. You can have the Z domain and the S domain, and you can see here that the sample time is 1 second, right? Because every second it changes the value, so it discretizes it. But I've got a couple more things I want to say about this, because you can do a lot. There's more cool stuff you can do with the Tustin. So I'll finish this next time, and I'm going to push the quiz off 1 week. Okay, the quiz will be due next Friday because I think the quiz does cover some of this stuff I didn't get to. Okay, so I'll see you next week. And Thursday is lab time.